back to the next slide deck of the training regarding the use of radar systems in the mining industry in the context of collision avoidance systems. What we are going to cover today and in the slide deck is, please don't be too frightened, the basic radar physics, math and geometry rules. I will try to keep it as simple and straightforward as possible, introducing the most important stuff and effects to understand the radar sensor feedback. To make it not too heavy, I put this slide deck into 3 parts. This is part 1, and let's get started. The purpose, and especially what we want to cover in this under section, is to understand what is a wave and especially what is a radio wave. Then we come to the question, why can I hear around the corner but not look around the corner? It might sound as a stupid question, but it has its reason. We will mostly compare the human senses to the senses, when you say so, of the machine as radar. Where are the differences in the perception, and where are the differences in the physical rules that underlie. Finally, we need to be able to answer the question, where can a radar see and where is a radar blind? If we can answer these 2 questions, then we can actually really understand radar feedback in the cabin of a machine and always be aware of what's happening in front, behind, or wherever around the machine covered by radars. So, radio waves explained in basic words. We remember radar stands for radio detection and ranging. Maybe you also heard about LiDAR, which is basically then light detection and ranging. Or if you're familiar with boats and submarines, sonar, sound navigation and ranging. What is the takeaway here? There must be something important about this radio. There might be other sensors and physical concepts used to be able to detect and range, but the radar is specific using this radio wave. Wave is simple. It's always when we go on vacation or free time activities, we know it from water bodies, the translation of movement in a medium in form of a wave. What does radio mean? It's also something that we know from our everyday work, especially from two-way radio. So something that is used in telecommunication, communication after all, and sometimes also to play music to make the work less monotone. What is the physical definition of a radio wave? It is an electromagnetic wave with a frequency between 10 by the times of 4 and 10 by the times of 12 Hertz. So I expect the next slide to explain what is an electromagnetic wave, what is a frequency, and what is Hertz. But let's go back to wave and then cover the rest. If I have the urge to throw a stone into a calm lake, I can see the wave propagation in all directions with the same speed and with the same power. So in the middle of a water body, there is a 360-degree omnidirectional expansion of waves versus a directional wave. This you can imagine as a bowl where I just, instead of throwing a stone into the middle, hit the boundary of this bowl or whatever, barrel, and then the waves propagate directional, because on the one hand side there is the hull of this body, and in the medium, in the water medium, the waves propagate again directional. This is water bodies, and there I can observe the speed of a wave, but this is not the case for an electromagnetic wave. Electromagnetic waves propagate with the speed of light, which is indicated by the letter c. And this again is the speed of 300 kilometers a second. 300 kilometers a second are very difficult to picture in front of the brain. It is basically the distance to the moon, a little bit more. The distance to the moon is a little bit more, 384,400 kilometers, which means if I could and would try to shoot the moon with a radar beam, it would take roughly 1 and a bit second to reach to the moon and 1 and a bit second to come back. So it would basically take like 2 seconds and a bit for me to actually see the moon as a reflection in my radar. Okay, we covered a wave speed. Let's cover wave frequency. A frequency translates into the repetition rate of this wave. So the wave body has up and down. At the point in time where it is on the same level where this wave started and with the same direction, I have the frequency and repetition. The guy who defined this was called Hertz, so he called this procedure after himself. 1 Hertz translates to 1 event repetition per second. So 10 by the times of 4 Hertz means 10,000 repetitions per second. And sometimes we also talk about gigahertz. Giga is nothing less than 10 by the time of 9, so 1 billion repetitions per second. With this knowledge we come to the maybe most complex and complicated slide in the deck, which is trying to indicate different electromagnetic wave frequencies and the spectrum. Let's start with the blue line. We can go to the left, we can go to the right. However, the more we go to the right, the wave frequency increases. So we start with 10 by the power of 4 and end by 10 to the power of 20. When the frequency increases, the wavelength itself is decreasing. So it's decreasing from 10 to the power of 4 to actually negative power of 12. On the left side of the spectrum, meaning we have rather lower frequencies and higher wavelengths, here are the radio waves, which we are talking about and are also including radar in this spectrum over here. We also have the microwaves, which are smaller than the radio waves and end up by the number of 10 to the power of 12 in the frequency. Going from here, we change to the light spectrum. It includes the infrared light and the ultraviolet light. And between these two, between infrared, which a human cannot see, and ultraviolet, which human also cannot see, there is the small spectrum of light, which is also an electromagnetic wave, that our human eye is actually capable to see the visible light spectrum. This also indicates or explains physics why on the top of the rainbow it's red and at the bottom of the rainbow it's violet, because it's between these two spectrums or spectra. However, if we increase further the wave frequency, go higher, 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 we come to the particle radiation, which is also electromagnetic waves. First we start off with X-ray, which we are using to scan for broken bones, and then we become really deadly by the gamma radiation, as it is, for example, emitted in nuclear weaponry. So we could also just have a basic rule of thumb understanding of the dangers of this radiation. When we don't want to use something that emits gamma rays and also are less powerful than the ultraviolet light that is actually causing sunburns, we are somewhere with our technology over here, which means you don't burn yourself if you stand in front of a radar, but you generally want to have the exposure to this sort of energy to the minimum. So I wouldn't install a radar right next to my head where it shoots waves into my body 24 hours in the day. But if I just be as careful as I am with ultraviolet light and the sunlight, I can cover and protect myself quite easily. As we know, blue exclamation mark on the top right, this is knowledge that I expect to be in the brains when we come to the questionnaires. So now let's compare machine-human interaction in a machine as we know it today, with a human eye and human operator and human brain, which can also rely on video cameras, which but again like work as the human eye, as a pair of eyes, for example, in the rear of your machine. And on the other hand side, the tomorrow, when we add radar to the system and then have an extra component, an extra layer, an extra spectrum of electromagnetic energy to see around the machine. We have the eyesight, which we must maintain. We can use mirrors and cameras to just have a bigger portion of the surroundings of the machine that we can see, and based on that we make the decisions based on the vision. If we add radar, we have the additional radar site at the portions of the machine where there are radars installed. The radar sensor system is looking into, but this is not enough. We also need some sort of display to translate this radar site back into what is capable for us humans to see and understand, as we cannot simply see like the energy or the beam of the radar itself. We need a display. And to make decisions, this display somehow needs also an understandable feedback. For example, if it sees an obstacle, that it also displays an obstacle at the position where we would expect it. I have some benefits on the radar side. What means the negative impacts that I have with my human eyes, which means I cannot see in complete darkness, or have limited vision in dark conditions. I'm also impacted by too much light when I'm looking into the sun, for example, in an incline. I am impacted by fatigue and distraction. If I go tired, my rate of eye closure is increasing. If there is somebody or something in my eyesight which is attracting my attention by just human triggers, I also tend to look into this direction, maybe for a very long point in time, being distracted from my task as a conscious driver. And I can also decrease my vision by medical conditions. Might be dry eyes, might be generally my age and my eyesight decreasing, but can also be the consume of drugs which are impacting my ability to see. Here the question would be, can a radar help or mitigate? Yes, it is completely the case, as we will learn on the next slides. Darkness, too much light, fatigue, distraction, medical conditions, thus is not interfering with the capability of radar technology. However, there are impacts that just decrease the functionality of the radar sensor system, which then need to be mitigated and aided by the human operator and the human eyesight vision. Let's dive deeper. So, when can I see? And in comparison, when does the radar see? When is the time only one of us can see? And when is the time we need the other person or the other technology? It's better to say technology. Already said, light conditions. Whenever my vision is decreased by light conditions, I can rely on radar because it is not interfered by any absence or too much light in a situation. The human eye needs a reflector. I can either see a light source itself, a candle, the sun, some lights of traffic, but I can also see the reflections of these lights somewhere else. I can see the moon, whatever a light mast is just shining onto. And as we learned already in part 1 of this presentations, radar rely on a reflector of the radar energy to actually see their surroundings as well. Both human and radars have a point of focus, a focus area where they can see best. The human eye can adapt focus. That's not really the case for the radar. It has a fixed focus area, which is basically in the front, and it, just as a human eye, sees less sharp into the edges of the field of view. The human eye creates 3D vision by having two eyes and an overlapping view with these two eyes. So the three-dimensional images are where the right eye and the left eye overlap in the field of vision. For radars, it can be special radars or more advanced radars only need one radar sensor to already have three-dimensional capabilities. The human eye needs maintenance and correction. What does it mean? Maintenance to keep the eyes moist and clear from dust particles and just this grain. And also the correction. For me, I'm wearing glasses. I need to wear glasses to have a good view, otherwise I'm lost. This is not needed on the radar side. You will not see a radar with a correction factor. However, I also yet did not see self-cleaning radars, so some mechanical lens that is automatically cleaning itself in front of the radar. I haven't seen it yet, so it requires some maintenance and especially keep it clean from accumulating dust, mud, and effects like snow maybe. Final point, the human eye can be seen as unlimited in distance, as we can see stars and galaxies far, far away. But of course, somehow we are limited in distance in the everyday use case, where at some point in distance we just cannot really make out shapes and have a real focus and surrounding awareness. This point of maximum distance can be more limited for the radar. So usually, from my experience in the concerns of collision avoidance in mining vehicles, radars have not as long distance view as a human operator. But this will also be covered in the logic of the radar installation itself. So where are we with our basic understanding? I hope that this is almost clear now, that a radar sensor system is basically to see as an eye. It is a sensor that is scanning the environment wherever it is pointing to. Unlike ships and planes, we don't have a dish that is turning and making a 360-degree all-way coverage, but we really need to have it like an eye, but it can be actually an eye in the back of the head scanning the rear of the machine. And radar is never just seen to be a single word. It's the system. A radar system can be also made out of 2, 3, 4 different sensors, and then I would need to place all the eyes around the machine. So far, so good. So, what is the perception used for? Again, I can also argue that a radar is like a camera monitoring system, good for two main tasks, which is blind spot detection, so especially the area that I cannot observe as an operator because it's blocked by machine parts. And the other one is to see in conditions that I'm not capable to see with my human eyes, where then also camera monitoring systems would be limited. When I cannot see through the fog, the camera cannot see through the fog. But, however, a radar can see through the fog. Perfect. Or dust. And when it comes to the comparison between camera monitoring systems, how they work in the darkness, and radars, how they work in the darkness, again, radars don't need night sight. Their view is just as good in any light condition. Perfect. Coming now to the most important question and understanding. Where can a radar see? Again, we need to see radar as a system of one or multiple sensors. Let's take first the top-down view. Every single radar as a sensor has a unique opening angle in the horizontal plane, which means it's open up to the left and it's open up to the right with a certain degree, which is different on the sensor. A company A maybe gives out a sensor which has an opening angle of 20 degrees to each side, or 30 degrees to each side, and 40 degrees to each side. And company B then maybe 25, 35, 45. Why so? It's simply because, depending on machine size, and also the operating logic of the machine, I maybe want to have a different opening angle. When I have an articulated machine like this wheel loader, I want to have a broad view to the rear because I can maneuver quite in short corners. If I take a rigid frame haul truck, however, maybe I want to have a very narrow view because I need to look far, far away, but not collide with machine parts. And so I would choose an opening angle that is narrower in the azimuth, which is called this plane. This is top-down view. And again, radar sensor system, off-highway truck maybe has multiple sensors also to the front, which then also might be a different opening angle required, or not a sensor at all in the front for the wheel loader. How is the situation in the side view? I also have an opening angle in the elevation, in the vertical plane, which could, but most probably is not the same value as the azimuth angle. Here it is also not always necessary to be symmetrical. What's more interesting for me is to look down to the machine, to look to the ground, to cut down the blind spot directly behind the machine. So I want to have a steep elevation angle to the ground, but it's not so important to have a steep elevation angle to the sky, especially for equipments like wheel loaders. Same is true for the side view at the off-highway truck, which is also capable of it's the necessity to hoist and open the dump body, which then can also interfere with the radar, and there needs to be some certain logic to either not collide constantly with machine parts, to have the logic of if the radar is getting some feedback from the hoist body, and so on. Long story short, where can a radar see? It depends on each single radar, its installation position, and the unique required azimuth and elevation angle in the direction the sensor is pointing to. So there is no rule of thumb, there is no easy bridge to remember. It is unique for each machinery, for each mine, for each equipment, for each radar supplier. With this we come to an end. We have the quick question check. I will not go through the reading through the questions here. You can do it in your speed. Just tick what you think is true, and I hope that it became clear. On the one hand side, the physics side, what is a wave? On the other hand side, where are the benefits that we need to work as a team when we operate with an equipment, with an operator and radars, because an operator can have, the person brings specific benefits to the table, but also some benefits are brought to the table by the radar, and if it works complementary, yes, it's a nice addition to see more what you are then usually keep missing. Thanks for your attention, and I see you in part 2 when we cover the question why I can see but not hear around a corner. Thank you.